Again, this is a continuation of our discussion of polynomial functions with a degree of 3 or more. I want to talk about what to do if the polynomial function cannot be factored. Then how in the world are we going to find the zeros or the x-intercepts? If you have a polynomial that has a degree of 3 or more and it's not factorable, then we use something called the rational zero or the rational root test. And what the rational root test does is it relates the actual possibilities of rational zeros to the relationship between the leading coefficient and the constant of the polynomial. You basically use a relationship that looks at the factors of the constant divided by the factors of the leading coefficient. Now, the constant is the value that doesn't have an x next to it, and the leading coefficient, remember, is the value that's in front of the highest exponent. And so then you look at that relationship, and it gives you a list of possibilities. The rational zero test only gives you a list of possibilities. It doesn't actually tell you which one it is. We have to figure out which one it is using synthetic division to actually find those particular zeros. So I'm going to show you how to use the rational zero test when you're working with these polynomials. A lot of the questions will look similar until we get to the point of finding the zeros, but we do start out, as we had before, looking at the degree. Again, the degree, just in case you've forgotten, the degree is represented by the letter n, and it corresponds to the highest exponent. And so in this case, that exponent, that high exponent, is a 5. So the degree is 5. My leading coefficient is the constant or the number in front of that highest degree. Now, when I look at this polynomial, you may think, well, there's not one, but remember, there is an understood one in front of that particular x. It's just not written. And then it asks us to use the leading coefficient test again. And so if I look to see what I have an odd degree. 5 is odd. And I have a positive lead coefficient. So if I go back and I look at the 4 options that I have, this tells me that it's going to fall on the left and rise on the right. The number of turning points, remember the formula is at most n minus 1 turning points. Well, in this scenario, if we figure n minus 1, okay, so that's going to be 5 minus 1 is 4. So I would have at most 4 turning points. Remember, at most means it's going to be 4 or less. 4 or less. Then it says, according to the fundamental theorem of algebra, how many zeros could you have? And again, remember, the fundamental theorem of algebra tells us that there's going to be exactly n zeros. So in this case, we would have exactly 5 zeros. Whoops, spelled that wrong. Sorry. Okay, then we can use Descartes' rule of signs to help us to determine how many of those zeros are going to be positive and how many of them are going to be negative. Okay, to make that decision for positive, we go back and we look at the original function as it was given to us, and we count the sign changes. So we go from positive to negative. There's 1. Negative to positive. There's 1. Positive to negative. There's another one. Negative to positive. There's another one. Positive to negative. So it's possible that I could have 5 or 3 or 1 positive 0. To decide whether we're going to have negative, we have to substitute negative x into the equation. So we have negative x to the 5th minus 8 times negative x to the 4th plus 28 times negative x to the 3rd minus 56 times negative x squared plus 64 times negative x minus 32. I'm having to squeeze it in there for you. Whoops, got that all messed up, didn't I? All right, so then you got to go back and do the calculations, okay? So we would have the opposite of x to the 5th minus 8x to the 4th minus 28x to the 3rd minus 56x squared minus 64x minus 32. And if you look there, you go from negative to negative, negative to negative, negative to negative, negative to negative, negative to negative. There's no sign changes. So that tells me that I'm going to have 0 negative possibilities. And that's going to be helpful to me in just a minute. Okay, so hold on to that thought. And then we move on. And again, the first thing we want to do here is find the y-intercept. And again, to find the y-intercept for any function, you let x equal 0. So I would have 0 to the 5th minus 8 times 0 to the 4th plus 28 times 0 cubed minus 56 times 0 squared plus 64 times 0 minus 32. So I'm going to have 0 minus 8 times 0 plus 28 times 0 minus 56 times 0 plus 0 minus 32. So I have 0 minus 0 plus 0 minus 0 plus 0 minus 32. So when I get through with all those zeros, I end up with negative 32. So my y-intercept would be the ordered pair 0, negative 32. And then this one specifically says find the zeros using the rational zero test, because I knew ahead of time, quite honestly, I don't have a clue how to factor an x to the 5th. Most of the time we only factor something, it's going to be x squared. So I don't have a clue. So we're going to use the rational zero test. So the rational zero test says look at the relationship between the constant, which in this problem is 32, and the lead coefficient, which in this problem is 1. And so I need to think about all of the numbers that I can multiply together and get 32. So I could do 1 times 32. I can do 2 times 16. I can do 4 times 8. And I believe that's it. And the thing is, I don't know whether these were positive or negative. So I have to allow for the fact that they could be positive or negative. And then I have to think about what can I multiply and get 1 in the denominator? Well, the only thing I can multiply together to get 1 in the denominator is 1. So then I have to think about all of those ratios or fractions. I'm going to have 1 to 1, 32 to 1, 2 to 1, 16 to 1, 4 to 1, and 8 to 1. And again, we still have the possibility we don't know whether they're positive or negative. So ultimately, I get this list: negative, positive, and negative 1, positive and negative 32, positive and negative 2, positive and negative 16, positive and negative 4, positive and negative 8. So what I've done is I have created a list. This is a list of possible zeros for my polynomial. If I didn't have that list, I would just have to randomly start guessing at what I think the answer is. And I could sit here all day and not come up with that answer. So I've gone from having a bazillion jillion possibilities to having 12 possibilities, because I have 2, 4, 6, 8, 10, 12. But, and here's where Descartes' rule of signs comes into play, guys. If you go back and look, we said, based on Descartes' rule of signs, we couldn't have any negative zeros. So that means that I can eliminate the 0 or the negative values from this list, and I realize I can only use 1, 32, 2, 16, 4, and 8. I can eliminate, I can eliminate the negatives because of Descartes' rule of signs. Okay, so I eliminate the negative options based on Descartes' rule of signs. So now I've narrowed it down to 6 options. And I got to try to figure it out. And the only way to do that is to use synthetic division to figure out which one of these is 0. Okay, so let me show you how to set up synthetic division in case you didn't catch on to that. All right, so the way you set up synthetic division is you draw a box, and inside that box, that's where you're going to put your possible 0, one of those values off the list. Out here beside the box, you're going to put the coefficients of the polynomial. Okay, so of your given polynomial, we had 1x to the 5th minus 8x to the 4th plus 28x to the 3rd minus 56x squared plus 64x minus 32. I don't worry about putting all the x's in there. I put just the numbers. And let me go back because I got my 64 messed up there. Okay. And then I'm going to leave a space, like one line, if I'm doing line to paper, and I'm going to draw an equal bar. Now, unfortunately, this is the one case where it becomes a little bit of trial and error. Okay. So maybe I'm going to start with the number 1. Okay, so here's how synthetic division works. You drop the 1, and then you multiply. 1 times 1 is 1. Then you add. Negative 8 plus 1 is negative 7. Multiply. 1 times negative 7 is negative 7. Add. 28 plus negative 7 is 21. 1 times 21 is 21. Negative 56 plus 21 is negative 35. Negative 35 times 1 is negative 35. 64 minus 35 is positive 29. 1 times 29 is 29. Negative 32 plus 29 is negative 3. Now here's the deal. When you're doing this synthetic division, what you want to happen is you want this last value to be 0. You want a 0, because if it's 0, that means you have found an X-intercept or a 0 for that polynomial function. Well, negative 3 is not 0, so that means that the positive 1 did not work. So unfortunately, that means I need to start over. Okay, so again, I put my box. I have 1, negative 8, 28, negative 56, 64, and negative 32. Negative 3, that's kind of close to 0. So the next number that I'm going to try, I'm going to try 2. Okay, 1 was close, and so I'm going to try 2. Okay, so I set it up. I'm going to draw my box and do the synthetic division. Drop the 1. You always drop that first number. Then you multiply. 2 times 1 is 2. Negative 8 plus 2 is negative 6. 2 times negative 6 is negative 12. 28 plus negative 12 is 16. 2 times 16 is 32. Negative 56 plus 32 is negative 24. Negative 24 times 2 is negative 48, plus 64 is positive 16, times 2 is 32, which gives me 0. So notice this time I get lucky and I get a 0. So that tells me that 2 is a 0 of the polynomial. Now, once you find one, don't stop there, guys, because now, see what's happened? You've basically divided this one out. This is like having x to the 4th, okay? And we got to find all 6 of them or all 5 of them, okay? How many are we looking for again? Go back, and if you don't remember, go back and look. We're looking for 5 zeros, okay? So, and the best thing to do, you want to make sure that the 2 doesn't have multiplicity, that it doesn't work again. Okay, and so the next thing I'm going to do is I'm going to start right here. I don't start over. I'm going to start at my answer, and I'm going to start right here. I'll draw me another box, and I'm actually going to try the 2 again, because it's possible that it has multiplicity, that it will occur more than once, and you can't see that on the graph. The only way you're going to find it is if you do the math or do this division. So drop the 1. 2 times 1 is 2, plus negative 6 is negative 4, times 2 is negative 8, plus 16 is 8, times 2 is 16, plus negative 24 is negative 8, times 2 is negative 16. And gosh, guys, look, I get a 0 again, which tells me that this particular value of 2 occurs a second time, so that it has multiplicity. Okay? Since it worked a second time, I actually need to check to see, will it work a third time? Again, you want to keep trying it until until it doesn't work anymore. And so I've run out of space, so let me copy this. I need this last line here, 1, -4, 8, and -8. Okay, so I'm going to write those down. Go back over here. I need 1, -4, 8, and -8. Let me make sure I wrote those down right. Okay, otherwise I'll mess it up. 1, -4, 8, and -8. 1. Okay, got them right. Okay, so here again, we're going to start where we left off. Okay, we're not starting over. And I'm going to try the 2 again. I want to keep trying that 2 until it doesn't work anymore. Okay, so do the synthetic division again. Drop the 1. 1 times 2 is 2. Plus -4 is -2. 2 times -2 is -4. Plus 8 is 4. Times 2 is 8. And gosh, guys, look. I get 0 again, which tells me that this 2 works a third time. So it's going to occur 3 times. But you can't, again, visually, you can't see that on the graph. Well, since it worked that time, I'm going to try again. Okay, I'm going to keep going until it doesn't work anymore. Okay, so I'm going to try the 2 one more time. Drop the 1. 2 times 1 is 2. -2 plus 2 is 0. 2 times 0 is 0. And I get a remainder of 4. Okay, so I get a remainder of 4. So that tells me that it doesn't work this time. Okay, so then I have this line right here. We started with an x to the 4th. Let me back up so you can see. Or excuse me, we started. This was x to the 5th. I'm going to write it in here so you can see it. X to the 5th. We took 1 out, so we had x to the 4th. We took another one out. That would have been x cubed. Okay, so this started as x cubed. So this gives me an x squared. Once I get this to a quadratic, now this is x squared minus 2x plus 4. That's a quadratic. Once I have a quadratic, remember, we can either factor or we can do quadratic formula. And I don't believe this particular polynomial factors, so I am going to have to do quadratic formula. So in the quadratic formula, A is the understood 1, B is the -2, and C is the 4. So I have x equals opposite of B plus or minus the square root of B squared minus 4AC all over, 2A, which gives me 4 plus or minus the square root of 4 minus 16 all over 2. That's 4 plus or minus the square root of -12 over 2. Okay, I'm going to go up here to the top so I can, let's see, so that gives me 4 plus or minus, I'm going to get 2I square root 3 all divided by 2. And one more thing, I can factor out this 2 in the top and then divide it out. Ultimately, I have 2 plus or minus I on the square root of 3. So I actually do, guys, it's on about 3 different slides here, but I end up with 5 zeros because I have 2, 2, 2. It occurs 3 times, and then I have 2 plus I square root 3 and 2 minus I square root 3. So I have 3 positives, and then I have the 2 imaginary for a total of 5. Okay, I want to try to do one more example so you'll have one of an odd degree and then one of an even degree. Okay. All right, so we begin again with what is the degree? In this case, the degree is 4. What is the leading coefficient? It's a positive 2. So I have an even degree and a positive lead coefficient, which means eventually it's going to rise left and rise right. Turning points is the degree minus 1. So if I go off to the side, I have 4 minus 1, which is 3. So that tells me that I have at most 3 turning points. The fundamental theorem of algebra tells me I'm going to have exactly 4 zeros, and then I'm going to apply or use Descartes' rule of signs to determine how many of those are going to be positive and how many of those are going to be negative. Okay, for the positive, we look at the original function as it's given. Okay, so we go from positive to negative. There's 1. Negative to positive. There's 1. Positive to positive. No. Positive to negative. Yes. So I could have 3 or 1 positive. To decide if you're going to have how many negatives you're going to have, you have to substitute negative x into the function. So I would have 2 times negative x to the 4th minus 15 times negative x to the 3rd plus 23 negative x squared plus 15 times negative x minus 25. And then I have to go back and do the math. Now remember here that when you raise a negative coefficient to an even, you get a positive. When you raise a negative to an odd, you get a negative. So I have 2x to the 4th plus 15x cubed plus 23x squared minus 15x minus 25. And again, if I look in that particular scenario at my sign changes, let's see, positive to positive, positive, right here, we go from positive to negative. So there's 1, negative, negative, no. So I could have 1 negative. Okay, again, to find the 0, remember we always to find the Y-intercept, we let x equal 0. So we would have 2 times 0 to the 4th minus 15 times 0 cubed plus 23 times 0 squared plus 15 times 0 minus 25. So I have 2 times 0 minus 15 times 0 plus 23 times 0 plus 0 minus 25. So I have 0 minus 0 plus 0 plus 0 minus 25. So ultimately, my y-intercept is going to be negative 25. So as an ordered pair, I would have 0, negative 25 as my y-intercept. Then as I'm looking at that problem again, I've got that 2x to the 4th. I can sometimes factor something raised to the fourth power, but in this case, I don't know how to do that. And so my only option for finding the zeros is to use the rational zero test. So let's get it set up here. My rational zero test, I'm going to look at my constant, which is 25, compared to the lead coefficient, which is positive 2. So then I got to think about the numbers that I can multiply together and get 25. I can do 1 and 25 and then 5 times 5. And again, remember, we don't know whether those are positive or negative. Then in the denominator, to multiply to get 2, what I multiply to get 2, I could have plus or minus 1, plus or minus 2. So I could have 1 to 1, 25 to 1, 5 to 1, 1 to 2, 25 to 2, and 5 to 2. Okay, so I'm going to have, and again, we don't know if those are positive or negative, so you have to allow for both possibilities. So ultimately, our list of possible zeros is plus or minus 1, plus or minus 25, plus or minus 5, plus or minus 1/2, plus or minus 25 halves, plus or minus 5 halves. Now, one thing that may help you, again, we've narrowed it from having a bazillion jillion to having 12 options, a couple of which are fractions that I know you guys won't really care for. But sometimes one of the other things that you can do to kind of help you, and so it's not a whole lot of trial and error with today's technology, we could actually create a graph using our graphing calculator and kind of get a sense of, okay, this is where I want to start looking for my zeros. So let me see if I can do that for you. Okay, so I'm going to enter into my calculator the function that we have. Okay, so I'm going to enter y equals 2x raised to the fourth minus 15x raised to the third plus 23x raised to the second plus 15x minus 25. And then I'm going to graph. Now I have the grid turned on so you can see it. And it's thinking about it. Okay, and I can kind of see, visually I can see 1, 2, 3, 4 zeros. And it looks like maybe one of them is at positive 1. This one over here looks like it might be at 5. And so if I can at least get a starting point, then I can go and actually do the synthetic division. So let's set up the synthetic division and give it a shot. Okay, so using the graph can also help you narrow those options as well. Okay, so visually I didn't see any negative ones. Okay, so I have my box. I have 2, negative 15, 23, 15, and negative 25. And it looked like on my graph that 1 was one of my zeros. So I'm going to try 1 first. Okay, let me draw my... Okay, so I have dropped the 2. 1 times 2 is 2. Plus negative 15 is negative 13. Times 1 is negative 13. Plus 23 is 10. Times 1 is 10. Plus 15 is 25. Times 1 is 25. And I do actually get, at the end, I do have a remainder of 0. So that tells me that 1 is a 0 of the polynomial. Now, Again, we should, at that point, double check and make sure that 1 doesn't occur again, that it doesn't have multiplicity. So I'm going to try that. Okay, so I'm going to try the 1 again. Drop the 2. 1 times 2 is 2, plus negative 13 is negative 11, times 1 is negative 11, plus 10 is negative 1, times 1 is negative 1, which gives me 24. So it does not work a second time, so it only occurs once. So I'm going to start where I finished. Okay, I'm going to write it down again. 2, negative 13, 10, and 25. It also looked like on my graph that the value of 5 was a 0. Okay, so I'm going to try the 5. If most of you would probably try to avoid the fractions if at all possible, so that's why I'm trying the whole numbers first, and that's probably a good idea, is to try those whole numbers first. Okay, so here we go. We're going to drop the 2. 2 times 5 is 10, plus negative 13 is negative 3, times 5 is negative 15, plus 10 is negative 5, times 5 is negative 25, which does give me that remainder of 0 that I'm looking for. Okay, so that tells me that 5 is a 0 of my polynomial function. And remember, we started with x to the 4th. I dropped it down to x to the 3rd, and now I'm down to 2x squared minus 3x minus 5. So I have a quadratic, and I possibly can factor or use the quadratic formula to find the rest of my zeros and not have to do this trial and error or synthetic division. So I believe, I'm going to come over here to the side, I believe this will factor. So I have 2x and x. I have 5 and 1. This one should be negative. And this one should be positive. Okay? So I know one of those had to be 0. So either 2x minus 5 was equal to 0, or x plus 1 is equal to 0. If I solve each of those respectively for x, let's see, I'm going to subtract 1 from either side first. So x is negative 1. And then the last one, 2x equals 5. Divide by 2, so x is 5 halves. So ultimately, we find that our zeros, and we should have 4 of them, and I do, okay, my zeros are 1, 0, 5, 0, negative 1, 0, and 5 halves, 0. And if I go back and look, let's double check ourselves. We said we could have 3 or 1 positive and 1 negative. Well, look, I have 1 negative and 3 positive. So I'm okay.